Good morning, everybody. So at the end of the last lecture, we were talking about queues. So we came up with an interface for a generic queue, right? So in our interface, we've got, so first of all, remember what a queue is, right? So a queue is a data structure where you add elements to the back of the queue, and you remove elements from the front of the queue. So we created an interface for our queue. It's generic, so we have a queue of any element type, right? And we've got the usual methods, right? So we have a size method. We've got an isEmpty method. Now enqueue and dequeue. So enqueue adds an element to the back of the queue, and dequeue removes an element from the front of the queue. Front and back just return the elements at the front and the back of the queue without changing the queue. Right? And then we implemented it with a list, right? So with a list, it's very straightforward, right? Internally, you have a list. So for enqueue, you add the element to the end of the list, just like in a stack, right? And in dequeue, where's dequeue? And in dequeue, you remove the element at the front of the list, right? So you remove element 0 from the list. Now the problem with this implementation is if you're using an array-based list, then that remove operation there is in big O of n, right? Because in a list, you have to, when you remove the first element of the list, you move all the remaining elements of the list forward one position. Right? So we'd like to implement a queue where dequeue is not in big O of n. And so we started to look, so now we're going to look at the implementation using an array. Right? So this is a little bit trickier than implementing a stack. Right? So with a stack-based array, it's pretty straightforward. You just have an array and you keep track of where the top element in the stack is. For a queue, it's a little bit harder. You need to keep track of where the front element of the queue is and where the back element of the queue is. Right? So remember, front and back, these are going to be the indexes into the array where the current front and current back of the queue are, unless the queue is empty, in which case the front and back don't necessarily correspond to the current front and back of the queue. Right, so for example, if you make an empty queue, then we have an array, in this case of size 16. Right? All the elements of the array happen to be null. Right? We're going to start with the front of the queue pointing at 0. So if there was an element in the queue, it would be in the first element. Right? And back is going to be pointing at, in this case, -1. Right? So we're going to use, so if you look at the picture here, you might think that, well, if the queue is empty, then the back element is, or the back field is always 1 behind the front field. But you're going to see shortly that's not the case. Okay, so if I want to add an element to the queue, then we want to add to the back of the queue. Right? Now remember, back is supposed to be pointing at the current back of the queue. Right? So back here is pointing at this thing that doesn't exist, right? So -1. So the way we're going to implement enqueue is we're going to move back 1 position to the right. Right? So step 2, move back 1 position to the right. And then we're going to set the element at that array location to the enqueued element. Right? So in other words, we're going to add the element to the new back position. Step 1 is if the array is full, we have to do something. So we have to consider expanding the size of the array. But we'll look at that in a second. So that's just going to happen like, that's going to happen in a way that's similar to the way we did it with a stack. Okay, so if we enqueue one element, right, back moves 1 position to the right, so it now points at the 0. Right, then we add the element into the array. We're keeping track of the size of the queue, so we have to add 1 to the size as well. Right, now notice back and front both point at the same element. Right, so when you have elements in the queue, back and front really do point at the current back and front element. So if we enqueue again, we're going to shift back 1 position to the right, and then we'll add the element into the new array location. Right, notice back is now in front of front, right? So back is moved to the right of front. Right, if we enqueue again, back's going to move 1 position to the right, and then we're going to add the element at that new location, right? And so on, and so on, and so on. Right, so there's the picture after 5 enqueue operations. Right, so to dequeue, we're going to remove the front element. Right, so we know what the current front element is, so we're going to remember what the front element is. So we're going to remember we have an A here. Right, then we're going to shift front 1 position to the right, right, to simulate removing the element from the queue. And then we're going to decrease the size of the queue, and then we're going to return the A. We're also going to null out that value there so that our array always, if the array If there's no element in that array location, we're going to null it out to indicate that there's no object stored in the array. Right? So we're going to remember what the front element of the queue is. Right? We're going to remove or overwrite the current front element. Right? So we're going to replace it with null. Right? We're going to shift front one position to the right, and then we're going to return the element. Right? Notice that when we, so notice that so when I showed you the picture in the previous lecture, when you dequeue an element, you move all the elements over one position to the left. Right? But you don't want to do that because that operation takes big O n time. Right? Because you have to move the n-1 elements that are that remain in the queue. So instead of moving all the elements, we're just going to shift front one position to the right. Right? And hopefully this saves us from the big O n complexity of dequeue. Right? So if we dequeue again, we're going to remember what the B is. We'll shift front one position to the right. We'll null out the B, and then we'll return the B. Right? So there it goes. Right? Dequeue again, so move front, remember what the C is. Move front one position to the right, null out the C, and return the C. Like that. And if you dequeue a fourth time, we now have the front and back both pointing at the E. Right? So the front and back of the queue, there's only one element in the queue, so they both refer to the same element. And finally, if you dequeue again, right, the E comes out, and now front is in front of back, right? It's to the right of back, right? Or back is one less than front, right? Which is what we had at the beginning when we made it the empty queue to begin with, right? It turns out, though, that you can't use that as a condition for the empty queue, right? So you're going to see shortly that you can have this situation, but the queue is in fact full. Right? So if we enqueue again, back moves to the right one position, fill in the value of the array, right? And now keep on going, right? So we enqueue a bunch more elements, right? And now notice what our problem is, right? Back now points at the last element of the array, but there's still empty spots in the array, right? So in other words, the queue's not full, or the array's not full, right? But back is at the last position of the array, right? Or points at the last index of the array. Right, so in order to keep on using the array, what we're going to do is, if you enqueue again, back is going to wrap around to the front. Right? So if we enqueue again, back wraps around to the front. Right? So when you shift one position to the right at the end of the queue, at the end of the array, you fall off the array and then pop back onto the front of it again. Right? The same thing is going to happen with front in a second. Right? So again, notice that back is now in front of front again. Right? So again, we have the situation where back is less than front, but the queue is not empty. Okay, so if you keep on enqueuing, right, then eventually back reaches the position that's one in front of front, and now the queue is full. Right? That's the exact same situation we had when the queue was empty. Right? So when you're in the situation, the queue is either full or it's empty, but you don't really know which is why we're keeping track of the size of the queue. Okay, so what happens to front, right? So if you start to dequeue the queue, right, then eventually front reaches the end element of the array, right? If you dequeue again, front's going to fall off the end of the array and show back up at the front of the array, right? So front also wraps around. So you're going to have to implement this wrapping around when you are implementing dequeue and enqueue, right? Okay, so if you take the array and connect the end of the array to the front of the array, you end up with what's called a circular array. Right? So for example, if I take what's the current front? So Q is currently index 0, right? And if I draw the rest of the elements in a circle, joining the end of the array to the front, you end up with what's called a circular array. And our implementation of a queue is essentially using a circular array. Right? So every time we enqueue, front goes one position clockwise, right? So front and back always move clockwise in this picture, right? So when you, dequeue, front moves one position clockwise. When you enqueue, back moves one position clockwise, right? And they just keep going around the circle. All right, so to implement this, to actually do the implementation in Java, right, you create your class. So we're going to call it ArrayQueue. We're going to implement the queue interface, and it's going to be generic. Right? So we have an array queue of elements of type E, right? That implements the queue interface for elements of type E. The default capacity, that's just some constant that represents the size of a default queue. So it's going to start, our array will start with a size of 16. Right? Just like in the stack, our array is a stack of, is an array of object, right? So that we can store any type in it. Right? Front and back, those will be our fields that store the current front and current back of the queue, as long as the queue is not empty. Right? And then size, that's the number of elements that are currently in the queue. So for the no argument constructor, we need to make an empty queue. Right? Now we have to make an array. So we create an array of the default capacity, right, and assign that to this ARR. We're going to set the front element. So we're going to set the front value to be 0, and we'll set the back value to be -1. Right? So again, just like the first picture. And the number of elements in the queue is 0, so the size is 0. If you want to copy another array queue, right, then what we need to do is we need to copy the other array queue's array. Right? So the easiest way to copy the other array queue is to use copy of. Right? So array is copy of, copy the other array, copy that many elements out of the other array. Right? And that will be the length of our new array. Right? So we can assign that new array to this ARR. Right? Copy the front and the back values from the other array, and copy the other copy the front and back values from the other queue, right? And the size of our queue is the size of the other queue as well. Okay, so for front, if the queue is empty, there is no front element, so you throw an exception, right? Otherwise, you're just going to return the element that's at this dot front in the array. Right. Now remember, our array has type big O object. Right? But front says that it returns an element of type E, so you need the cast here to placate the compiler. Right? So you have to tell the compiler that, hey, the array really does have elements of type E, so you need the cast here. So the back works the exact same way, right? Except you return the element at this back. Okay, so for DQ, you're going to remember what the element is at the front, at the current front of the queue, right? So that's going to be elem. At the end of the method, we're going to return that element, right? And so again, because the type of elem is object, we have to cast it to E when we actually return the value. Right? Then you're just going to follow the steps on the slides, right? So you null out the value stored in the array, right? So you set this array at this front to null. Now for front, we want to move front one position to the right, right? But we have to take care of this wraparound when it hits the end of the array. So you could do this with an if statement, right? So you could write this front equals this front plus 1. If this front is equal to the size of the array, this front equals 0, right? But it's easier just to use the remainder operator, right? So add 1 to this dot front, like that, right? And then divide by the length of the array and compute the remainder. Right? So if this front plus 1 is the size of the array, or the length of the array, then when you divide it by the length of the array, you get back 1 with a remainder of 0. So that automatically wraps it around. Right? And so the remainder operator is very useful when you want to wrap a value to a range between 0 and some other value. For the size, you just decrease the size by 1, and then you return the element. Right? And away you go. Okay, so for for enqueue, we have the situation where when you enqueue into a full queue, you have to resize the array. Now resizing the internal array is a little bit trickier for a queue than it is with a stack. Because in our queue, we're using a circular array rather than a plain old array. Right? So consider the following situation. Right? So at the top, I've got a full queue. Right? Notice front and back, they're somewhere in the middle of the array. So they're not at the front's not at the front and back's not at the back. Right? Now what happens if I just use array's copy of on that array? Right? Well, I make a new array, so there's my new array. Right? The elements from the old array get copied into the new array. Right? Naively, you'll copy front and back so that they also point to the same two elements. Right? But notice what happens at the first element of the expanded array. Right? So over here, you've got space to add more elements. Right? So back should be pointing at the P, Well, sorry, if this was a correct, if this was, if the elements in the, if you ignore the order of the elements in the queue, then back should be pointing at P, so that when you move back one to the right, you start to use up the new, the empty array positions. But that's not correct, right? Because back is over here, right? So you want to insert the next element after the U, right? But if you do it this way, you run into this problem. So you can't copy the array in one shot using array's copy of in this case, right? So what you have to do is you have to expand the size of the array, and then you have to copy in the elements from the old array into the new array in some sensible way. There's lots of ways you can do it, right? But the easiest way to do it is to take the front element of the old array and insert it at element 0 of the new array, right? Then take the second element, or the element after the front, and insert it at index 2, right? And then take the H and insert it at index 3, and so on and so on and so forth. U will end up at index 15, right? And now back will be the last element of the array. Well, I guess back will be 15 and front will be 0, right? So what you need to do is you need to unwind your circular array, right? It doesn't matter how you do it. There's lots of ways you can do it, right? So for example, you could take front and copy it into index 5. You could take index 6 and copy it in index 6, right? But when you get to index 0, you want to copy it into index 16, right? And then 1 will copy into 17, and so on and so on and so forth, right? So it doesn't actually matter how you unwind the array, but you have to unwind the array somehow. Right? So that's the easiest way to, I think that's the easiest way to do it. It's also the way that probably makes the most sense, right? So you unwind the array and you end up with the front of the front points in the new array at the first element of the new array, and back points at the index 15 of the new array. Right? Now when you add elements, they go into the correct spot in the new array. Right? So enqueue. So this is the if statement up here. That's all the resizing. So ignore that for now. Right? So let's assume you have space in the new array. Right? So, or in the array, sorry. So for back, you're going to move back one position to the right. Right? So this back equals this back plus 1. But again, you have to worry about wrapping the value of back if it hits the end of the array. So again, just take the just compute the remainder after dividing by the length of the array. Right? And that takes care of the wrapping for you. Once you have the new back value, you can set the array at that value, or that index, to the enqueued element. And then you increase the size of the queue by 1. So in the if statement, this is where we take care of resizing the array, right? So if the size of the queue is equal to the length of the array, then the queue is full. Right? So I have to make a new array. So we make a new array of object, right? The size or capacity of the new array is equal to the old array length times 2 in this case, right? And remember, you can multiply by any value bigger than 1. But 2 is convenient here. Next, you're going to copy the elements from the old array into the new array, taking care to remember that you've got front and back, right? So front and back might be in the middle of the old array. Right? Okay, so for my index I, right, that's going to be the index into the new array, right? So I can write temp I here equals something, right? Now for the index into the old array, right, that's just I plus front, like that, right? But you have to remember that that index wraps around, right? So again, I can take this front plus I, take the remainder after dividing by the length of the array, and that gives you the correct index in the source array, right, or in the old array. Right? So you have to be a little bit careful here when you define this index, right? You can define the index into the new array. You could also define the index into the old array, but it's trickier to write. Right? It's much easier to write it with the index into the new array. And there's enqueue. So that's a complete minimal queue implementation. Right? So in Java, you would also consider implementing methods like equals and toString, hash code if you're overriding equals. And then you might consider adding other methods as well. Right? So for example, we implemented a copy constructor way back at the beginning here. Right? So there's our copy constructor for array queue. Right? So this is the constructor that can copy another array queue. Right? But remember, we're implementing an interface now. right? So we're implementing the queue interface. So it might be nice if I can make an array queue by copying another queue, right? Where the other queue is not necessarily an array queue. Right? So in other words, I might want the copy constructor array queue, right? Now queue is the interface type, right? It's not the type of any specific queue, right? So I don't know if it's a list-based queue or an array-based queue or in a second a node-based queue, right? So I don't know what type of queue it is anymore. And so the question is how do you implement this constructor now, right? Because all you can use in this constructor are the methods that are defined in the queue interface, right? You don't know the internals of the queue that you're copying, right? So it's not as simple as copying the other queue's array because you don't know if it has an array or not, right? So you're now in the situation where you want to copy this other queue, and additionally, you don't want to permanently change that other queue, right? So in a method like this, where you take in an object as one of your arguments, right? You want to avoid modifying the state of the input argument, right? So in other words, you want your constructor in this case to avoid having any side effects, right? So you don't want to destroy the other queue at all or modify the order of the elements permanently or anything else, right? You would like the other queue to remain intact, right? And the caller of your method, of your constructor in this case, sorry, probably wants their queue to remain intact as well, right? They don't want you to copy their queue and destroy their queue at the same time. So the other requirement of this constructor is you have to leave that queue intact, right? And so I will leave you to think about how you might implement that method, that constructor, right? Similarly for equals, right? If you were to implement the equals method, it's pretty straightforward. It's relatively straightforward to implement equals where you check if two array queues are equal. But the question is can you implement equals so that an array queue can be equal to another queue, right? Again, you don't know the type, the exact type of the queue that you are comparing against, right? So you don't know what fields it has. And also, again, you don't want to change the other queue that you're comparing to, right? So again, objects should not have any side effects on the input argument, right? And so I'll leave you to think about how you might implement that as well. It turns out it's the same trick in both cases, right? So sometime after class, think about how you might go about implementing those two, that constructor and that method. And then you can do the same exercise for stack, right? We didn't do this, but in the stack, for our stack interface and stack classes, you can ask the same question, right? Can I make a new, say, array-based stack given another stack, right? Where I don't know what the innards of the other stack are, right? Can I take an array-based stack and ask if it's equal to another stack, again, where you don't know what the internal fields of the other stack are, right? The answer in both cases is yes. Right? Okay, any questions about array-based queues? What's that? Two. That was 2. This is 3. Okay, so just like a stack, we can implement a queue. Also, oh wait, sorry. There's something I forgot to talk about. Where is here? Okay, so remember one of the reasons for making this array-based queue is because DQ, where's DQ? Sorry, NQ. No, DQ, sorry. No, wait, sorry, NQ. Wait, all right, so one of the reasons for implementing the array-based stack, array-based queue is because DQ for the list-based stack was ON, right? Now, if you look at DQ for the array-based queue, what is its complexity, right? So there's an if statement here, there's an assignment here, array access here, plus assignment, right? Another assignment here, and then a return statement, right? So there's nothing here that depends on the size of the array. So DQ for an array-based queue is in O1, right? Which is much better than the ON we had for the array, array list-based queue, right? Now, there's nothing preventing you from going back to the array-based queue and implementing it like this, right? So you now go back to the array-based queue and modify it so that the array-based queue also has O1 complexity for DQ, right? What about enqueue? Right, so enqueue, you always run into this problem with these array-based containers where you might have to expand the size of the array. Right, and so enqueue is always worst case big O of n. Right, expand the size of the array and copy all of the existing elements. Right, so that's always O n. So the question is can I get O1 complexity for both enqueue and DQ? Right, and so the answer is you can, but you have to go to a node-based implementation. Right, just like we did with the stack. Right, so if you switch to a node-based implementation, right, so remember in a node-based implementation, each node holds an element, but it also holds a reference to the next node in the sequence, right? Then the implementation is very similar to how we implemented a node-based stack, right? The main difference is, right, in a stack, the nodes were added at the front of the chain of nodes. Right, so every time we pushed an element onto the stack, it got added to the front. Right, queues are always added in a queue. You've got stuff happening at both ends of the queue. Right, so when you add an element in a node-based queue, we're going to add it to the end of the sequence of nodes. But when you remove an element from a node-based queue, you're going to remove the first element in the chain of nodes. Right, so remember this is how stack. Oh wait, I guess what did this say? Nodes were added to the front. Okay. Right, so in a node-based stack, right, when you had so in a stack of size 0, when you add the node, right, you end up with one node in the stack. Right, if you push a second element onto the stack, right, you make a new node, right, and add it to the front of the stack, or sorry, for the front of the sequence. Right, if you push another element onto the stack, right, then you make a new node, hook it up to the front of the sequence, and away you go. For remove, or for a pop, right, you're always removing the first element in the sequence, right? So that's the same for a queue. So for DQ, you're going to remove the first element. For queues, though, when you enqueue, you always do it at the back, right? So not only do I have to keep track of the front node of the queue, I now need to keep track of the back node of the queue. Right, so here we have front and back, both referring to the first to the one node in the queue, right? If I enqueue again, I'm going to make a new node, right? I'm going to hook the current front up to the new node, right? And now you've added the element to the back of the queue, right? If you enqueue again, I'm going to make a new node. I'm going to hook the current back of the queue up to the new node, and then I'm going to advance back, right? And so on and so on and so forth. Right? So in our linked queue, right, the fields of our class are going to be the size, right, the number of nodes that are in the queue, right? Front and back, these are references to the current front and current back of the queue, right? They'll be null if there are no elements in the queue. Right? Just like the stack, internally we're going to have a node class, right? And just like, so the implementation is exactly the same as in the stack class, right? Because it's just a linear sequence, right? So inside each node, there's an element of type E, right? There's a link to the next node in the sequence, right? We've got a constructor that lets you set both the element and the link at the same time, right? So, because that's convenient. Okay, for the empty queue, right? So in the empty queue, the size of the queue is 0, right? There is no front or back node, right? So they're both null. Now, you have to be careful with these, right? So if you try to use front or back and they're equal to null, then when you try to use them to call a method or access a field, that will throw an exception, right? So you have to be very careful in your implementation never to do something with a null node. Okay, so what about front? So front's easy, right? I need to return the element at the front of the queue if it exists, right? So I know what that element is because I have a reference to the front node. Right, so the element in the front node is just this.front.elem. Right, and back is also easy because I have a reference to the back node. So I can just return this.back.elem. Okay, so what about enqueue? Right, so let's go back to the picture. Right, so in enqueue, I'm going to make a new node, right? So I'll make the new node B, right? I need to hook the front node to point to the new node, right? And then I need to adjust back so that it points at the new node. Okay, so here's enqueue, right? I make my new node, right? I store the element in the new node, right? Now the new node, that's going to be the back node. So its next field points at nothing, right? There's nothing after the new node, so we set that to null, right? Okay, ignore the special case for now, right? And so ignore the first two. I don't remember if there's something wrong, if there's something unnecessary on this slide or not. All right, let's just go with what's on the slide. I think you can simplify this. So ignore the first two cases, right? So the first case here, for the first line here, we make our new node, right? I now need to hook up back here, right? So when you make your new node B, you need to take the current back element or back node and hook it up to the new node, right? So I need to take the current back, right? The current back node and set its next field so that it points at the new node, right? So I have to write this dot back dot next equals n, right? And then I need to adjust the current back node, right? So the current back node then becomes your new node, right? You've added an element to the list, so you have to increase the size of the list. You've added a new element to the queue, so you have to increase the size of the queue by 1. Okay, so there are some special cases in this implementation, right? So if your queue is empty, right? Remember, there is no front or back node, right? Here I'm adjusting the back node down here, right? So I'm assigning to this dot back, right? But if the queue is empty, right, you have to remember to set this dot front as well, right? Otherwise, when you try to dequeue the queue, front will be null, and you'll end up with an exception of some kind, right? So you have to remember to set this dot front to n, right? If the size of the queue is 1, you've got another special case, I think. This front. I wonder if that's true. I have to go back and check if this is true. So if the size of the queue is 1, right, you also have to make the front node, right, you have to make it point to the next node as well, right? Because you've adjusted this dot back here, right? But now you need to adjust this dot front as well, right? So you also need to make that modify to, you have to make that refer to the new node that you just added as well, right? So there are these special cases that you have to watch out for. It's a bit tricky when you implement these node-based structures, right? You're always looking out for these special cases. Okay, so for dequeue, if the queue is empty, you can't dequeue the queue. So you throw an exception. Right, now let's go back to the picture again. So when I want to dequeue this queue, right, I want to take that front element off the queue. Right, so I need to remember what's in the front node. So I need to remember there's an A there. Right, I need to make front point to the next node in the sequence. Right, so I need to adjust front so that it points at front.next. Right, and then I have to watch out for the special cases as well. Right, so step 1, remember remember what's the current front element of the queue, because I need to return that element. Right, now I need to adjust this dot front. Right, so I want to make this front refer to the next node in the sequence. The next node in the sequence, though, is just this dot front dot next. Right, and so that adjusts the front field. Finally, you can you can decrease the size of the queue by 1. Because we have removed an element from the queue, right? And now you end up with a special case again, right? So if you take all the elements out of the queue, right? So in other words, if you dequeue a queue of size 1, your queue is now empty, right? But because up here we're only adjusting the front node, or the front field, right? In the case where the queue becomes empty, you also have to adjust the back node. Right, because now the back node also disappears, right? So the back node now gets set to null to indicate that the queue is in fact empty, right? And finally, you can return the element that you removed. Okay, so let's look at dequeue and enqueue. So if you look at dequeue, right? And you ask, what is the complexity of DQ? Right? There's a condition here, right? Assignment, assignment. I guess you can argue that's assignment, right? Condition here and assignment, right? So there's nothing here that depends on the number of nodes in the queue, right? So DQ for a node-based queue has complexity O1, right? Constant time. And the same is true in enqueue, right? Assignment here where you make a new node, right? Condition here, assignment, condition here, assignment, condition and assignment, and then assignment and assignment, right? So again, nothing here that depends on the size of the queue, right? So this is also in O1. So now you've got a queue that has complexity big O1 for both of its primary operations, right? So the worst case complexity for enqueue is better than in an array-based queue, right? So in an array-based queue, when you expand the size of the array, you have ON complexity. Right. For DQ, the worst case complexity is the same for an array-based queue. Right. Now, if you actually were to try to time these two implementations, it's hard to do well, but if you actually try to time how much time it takes to use these two queues, right, you would find that your node-based queue, even though its worst case complexity is better than the array-based queue, the average case runtime, so the actual amount of time you spend running your program, is slightly worse than in an array-based queue, right? And if you go look at the implementation, you can see why, right? So in enqueue, you have to make a new object, right? It turns out that in Java, that's a little bit expensive, right? So it's not like making a new primitive value, right? To make a new object, you have to allocate some memory, you have to set some fields, you have to return the value back, and so on and so forth, right? So a lot happens when you call the constructor and new, right? And then you have a bunch of assignment operations, right? But in an array-based queue, right, all you have are a bunch of assignment operations on an array. So it turns out that it's slightly faster to use an array-based, it's probably slightly faster on average to use an array-based queue for enqueue. Right? For DQ, the complexity and the actual runtimes are roughly the same. Right? So yes, it's true. Your worst case runtime is in fact better, right? But you might find that if you have a really, really, really demanding application, an array-based queue might be slightly better. But you'd actually have to time this to find out if that's true for your situation. Okay, so that wraps it up for queues. Any questions on either of the two implementations? All right, so the next topic. Generic methods. So we've created a generic interface, right? So an interface where there is a type as a parameter. We've created a generic class, right? So again, a class where the type is the parameter. So is it possible to make a generic method? So can you write a method where the method also has type parameters? And the answer is yes. Right? So a generic method is a method that has its own type parameters, right? These don't have to be the same as the generic parameters of the generic type variables that the class has, right? So you can have a generic method inside of a generic class. For the sake of simplicity, I'm not going to do that because you end up with these types flying around all over the place. So I'm going to make it simple. We'll create some generic methods inside of a non-generic class. Right? Now, if you have a generic method, right, your type variables are independent for each method, right? So it doesn't matter if you always reuse the same type names for each generic method, they're independent anyway, right? So the scope of your type variables, they're confined to each individual method, right? And you'll find these generic methods in all sorts of places in the standard library, right? So arrays, the utility class that operates on arrays has a bunch of generic methods, right? So you can write a method that works on any type of array, right? Collections is the utility class that operates on sets and lists. So again, it's easy to write methods that operate on any kind of set or list, right? And objects is the utility class that operates on objects of type big O object. And it turns out it's also useful to have generic methods there. Okay, so like a generic class, a generic method doesn't look really any different than any other method, except you've got these type variables inside these angled braces. Right? So I want to make a utility class that operates on stacks, right? So our stack doesn't do very much. Our stack class or interface doesn't do very much, right? You can push or pop an element onto a stack, but you can easily imagine situations where you want to do other things with stacks. Right? So for example, I want a method that clears a stack, right? Removes all the elements. That method's not in our interface. We didn't put it in our stack class. So if you're using a stack and you need to clear it, you've got to write your own method to clear the stack. Right? Now, to clear a stack, you don't actually care what element appears in the stack, right? So to clear a stack of integer, it's exactly the same as clearing a stack of string, right? The actual type doesn't matter. So how do you implement this method? Well, it looks like this. Right? So here's my class stacks. Right? So it's going to be, whoa, sorry. So it's going to be a utility class that operates on stacks. It's a utility class, so all the methods are static. Right? Notice that the class itself is not generic, so there's no generic type parameter here. Right? You could put one in. It doesn't make sense to put one in this case. Right? But if you're in the situation where you're implementing a generic class, right, it's fine to have generic methods inside a generic class. Okay, our clear method, though, is generic. Right? It wants to be able to take in a stack of any element type. Right? And so for our purposes, the way you would write this is as public static, and there's your method, right? So void clear takes in a stack, right? And your generic type appears before the return type. Right? So it's always in front of the return type here. So in this case, it's in front of void. Right? How do you implement clear? Well, you just pop the stack until it's empty. Right? So as long as the stack size is greater than 0, or as long as the stack is not empty, pop the stack. Right? And eventually that will remove all the elements from the stack, and you'll have an empty stack. Right? And so that method. So there's an example of a generic method. Right? This one's not a particularly useful example because we never actually use the element type t inside the method. Right? But this would be a perfectly acceptable way to do this. Okay, so what's the complexity of this method? It's big O n, right? At least big O n, right? So if pop is big O1, this pops n elements from the stack, so that's big O of n. Right? If you are actually inside one of these stack classes, right? So if you're in the array-based stack, right? You could clear an array-based stack with basically 1 or 2 lines of code. Right? All you have to do is adjust this dot top to equal -1 and set size to 0. Right? So if you're actually inside of one of these classes, it's easier to implement the clear method. Right? And it's faster too. Right? So in an array-based stack, you can clear the stack in 1 step, so it's O1. Right? In a node-based stack, right, all you have to do is set the top node of the stack to null. Right? And that clears the stack as well. Right? So that's also O1. So when you do this sort of thing, it's not unusual that the complexity of your methods is worse than if you had these methods in the classes themselves. Okay, what about push all? So I want to take elements from a collection or some array, right? And I want to push all of those elements onto a stack. Right? You don't want to remove the elements from the collection or the array. Right? Now, in this case, right, the element type that's in the collection or array matters. Right? So if I have a list of string, I should not be able to push those elements onto a stack of integer. Right? So type safety is important here. Right? So in this case, I want to make sure that the type of the element in the collection also matches the type of element in the stack. Right? So by match here, I mean exactly the same. There's a question mark here, but I'm going to leave the question mark unanswered. Right? So here we have push all. Right? So I would like to push all the elements from a source collection onto a destination stack. Right? The element type in the collection must match the element type in the stack. Right? So that T and that T are the same in this case. Right? And so now our generic type T actually matters. Right? I need this generic type in order to enforce the constraint that the collection type and the stack type are in fact the same. Right? Internally, the type doesn't matter. Well, it sort of matters. I need the element type here in the loop. Right? So to implement the method, it's pretty easy. right? I iterate over the collection. So for each element in source, push the element onto the destination stack. Right? And so this method here, this is a nice example of showing the power of interfaces and substitutability in Java and generics as well, right? So here, right, I don't care what type of collection this is, right? It could be an array list, it could be a hash set, right, or a hash set or a tree set or anything else, right? Any kind of collection works, right? And I can push those elements onto a stack. Right? I don't need to write a separate method for lists. I don't need to write a separate method for sets. Right? I don't need to write a separate method for array lists, and so on and so on and so forth. Right? Any old collection will do. Right? And this all works because of polymorphism and substitutability in Java. All right. So, well, let's do the last method here, and then we'll call it a day. Right? I now want to implement a pop all method. So I'd like to take all the elements from my stack, remove them from the stack, and add them to a collection. Right? But I don't want to modify the collection otherwise. Right? So I don't want to clear the collection and then put the elements from the stack onto the collection. Right? I just want to add them to the end of the collection. Right? Again, type safety matters. Right? If I'm popping a stack of integer, I shouldn't be able to add those to a collection of string. Okay, so here we've got pop all. Right? It takes elements from a source stack and adds them to a collection, a destination collection. Right? Again, the element type of the source and the collection should match. Right? And again, this is easy to do. Right? So while your stack is not empty, or while the source stack size is greater than 0, just pop the stack and add the element to the destination, and away you go. Right? So again, relatively straightforward to do. All right, so we'll call it quits there. In the next lecture, we'll look at a more complicated method that requires you to do a lot more work in order to get it to, in order to implement it fully.